Thanks everybody for coming to join us for monitoring GPUs on Kubernetes. We're going to be using Prometheus Alert Manager and some interesting tech to get this going. So just a little bit about us. My name is Zach, and I'm here with Diane. And as you mentioned, we work in the CTO office in the AI group. Diane's our resident expert in performance engineering and in the AI group, and she focuses on analyzing performance data with ML.
And Zach is the lead for our log anomaly detection service, and he's currently working with optimizations and observability for our ML platform using Tensorflow and Spark.
So we're going to go over a little bit of a story, and then we're going to go over some core concepts on GPUs, CUDA, some interesting things in Kubernetes. We'll show you some examples you can take away when you can try at home, running Jupyter with GPUs on Kubernetes, and some examples of running NVIDIA SMI. And we'll have a live demo at the end, doing object detection with Facebook's Detectron on the NVIDIA V100 GPU. So, I watched this very interesting presentation by Elon Musk when he talked about, how he designed his factory. And he described it as the machine building machines, right? And one of the bottlenecks and challenges were their production of Teslas, how quickly if a customer would order a Tesla, how quick they could deliver it. And they found that when they were designing this, they found some challenges in their production. So one very interesting talk that he did was, he talked about, when you're designing the factory, you should design it like an advanced computer. And then look at engineers that think in that way, where they'll look at the pipeline and look at how you can improve the performance of the overall system. In that same way, when we're running on Kubernetes and we're building ML platforms, we want tooling that would give us a way to measure how our hardware is performing and how much is being utilized, and also for cost reasons as well. We want to save some money. So why is deep learning a big deal, right? It's disrupting a lot of industries, right? I saw the keynote yesterday or earlier today from Netflix when they were talking about how they're giving feedback to film producers on their films, and kind of giving them some information about their audience. And that's very interesting, and it's opening up a lot of industries that didn't really exist before. And then the whole self-driving, and then the voice assistant, and image recognition, with the facial recognition with the iPhone. And there's a lot of innovation that's happening, and these deep learning, frameworks and building deep learning stuff sometimes it can take a really long time, and then there's really good hardware that you can use to kind of improve the performance of the training runs. Very interesting, real quick, CPUs, you can see that they kind of plateaued. They haven't really improved a lot in terms of performance over the years. And then GPUs kind of have skyrocketed. This is a pretty old comparison, but the newer GPUs have even more than 2,000 CUDA cores. They have the K80 has about 4,000, or about a little bit over, about 4,000 and something CUDA cores. And then when we look at CPU clock speed, right, you'll see that the CPU clock speed kind of plateaued over the years and hasn't really improved significantly like how it used to improve on. But whenever you're building systems, you can still utilize parallel processes. Modern programming languages let you spin up processes spit up threads, and then you can utilize the CPU cores more efficiently by utilizing that. And then very interesting thing is the GPU has a different architecture and core count. We'll go over a little bit more of a comparison of the GPU and the CPU in a later slide. TensorFlow, you can run it on a CPU, but there are some optimizations you can make when you're building your wheel file. And then when you're running TensorFlow on a CPU, it'll actually tell you that your CPU supports certain flags, and then you can try and build your wheel file and try that. There's also community wheel files that currently exist already. The flags for CPU are all in the proc directory. You can find all your flags there. Just recently, Google merged a PR from Red Hat where we have our CPU and GPU builds of TensorFlow on Red Hat Linux 7.6, CentOS, and Fedora. And it includes CUDA 10.0, Python 3, and Python 2. So hardware accelerators, right? So you can either use GPUs or TPUs for accelerating TensorFlow. In terms of GPUs, you don't if you're using NVIDIA GPUs in particular, you can still do hardware optimization, or you can do optimizations to your program and utilize the GPU on a ML framework, but you can also do it general purpose. So if you just want to have a regular program that utilizes the GPU, you can use CUDA library. I believe there's bindings for C++ and there's a wrapper for Python, and also OpenCL if you want to use non-NVIDIA GPUs, if you want to run on something like an AMD. But for ML, typically you'll be using CUDA. As when you're running ML stuff, that's the main most popular one. So for our requirement, we wanted to reduce the latency. We wanted to look at increased bandwidth and increased throughput. So if we put CPUs and GPUs side by side, you'll see that a modern CPU like the Zen 5 has about 74 cores, and then K80 has about 4,992 cores. It's not exactly the same type of cores, but I mean, it's designed, like with the GPU, is designed to do more throughput, more so than the CPU. CPU is more for more focused on latency. CPUs are more energy efficient, and we'll go into more detail on CUDA. So CUDA, it's a proprietary tooling. You'd have to have a supported graphics card in order to use CUDA. A lot of frameworks currently utilize CUDA to utilize the hardware acceleration. In fact, when you're building TensorFlow, you'd actually have to have CUDA on the actual machine that you're running on, and have those libraries available when you're building your TensorFlow wheel file. And you get about a 10, depending on what you're running, but we have an example that we ran, and we get about a 10 times faster performance, or a little bit more than that. So on Kubernetes, this is just a visual of what the stack would look like. You have your server, you have your physical hardware, the GPU, and then you install an OS, and then you install the drivers, and then the container runtime sits on top of that, and then you have the CUDA libraries within the container, and the TensorFlow wheel file installed with, if you want to use Jupyter, you can, or you can just run TensorFlow on its own. So currently, the one motivation for kind of the tooling that we built out was because the current tooling that exists is NVIDIA SMI, which is terminal-based. We wanted more of a visual tool, and we wanted alerting. This is how the architecture looks like. So we have a node exporter that exports all the metrics about the GPU. Certain metrics, the important ones, which are the duty cycle, the memory being used on the GPU. So the GPU has its own separate memory, aside from what's provided in the actual server. And then we have a push gateway just in case if you do have TensorFlow jobs, and you can push custom metrics there. The interesting thing with this architecture actually is if you're running on cloud, for example, you may want to get alerts on if your GPU isn't really being utilized. For example, you can say, in 10 minutes, if my GPU isn't being utilized, I want to get a notification. And this is Alert Manager. It has a UI. But if we look at the previous slide, you'll see you can get an email, you can get a chat message, you can get a webhook that gets hit. And GPUs can get expensive on the cloud, so you might want to scale down your GPU node if it's not being utilized. So we have an example of we ran the same TensorFlow code side by side, and one with a GPU, one with a CPU. The GPU one finished in about 12 seconds, and the CPU one finished in about 152 seconds. So TensorFlow, if you want to run TensorFlow on a CPU on Kubernetes, you could literally just write this pod, specify the Docker container. But if you want to run it on a GPU, you would need to utilize the resource. Specify in the resource the nvidia.com/GPU1. That lets a scheduler know you need a GPU assigned to this pod. So this pod will get some libraries mounted. It'll get the devices available to use in order to utilize the GPU. Let's say you have different types of GPUs. Let's say you have a V100, which is more expensive, and then you have the K80, which is less expensive. And then for the more critical, more important stuff, you want to schedule on the V100, and then the less critical, you schedule on the older GPU. You could use node selectors and select which GPU type you want to use in Kubernetes. If your system admin hasn't set up good labels, you can relabel your Kubernetes nodes. So then when you're running on Kubernetes, you need training data to do your ML, right? Sometimes training data can be pretty big. And then Kubernetes has different plugins for different storage providers. So you can load your data in via NFS, Azure File, Ceph, FS, different cloud providers, and then load it into Kubernetes pod, and then train your ML on there. We have an example actually using NFS that you can try out. Basically, the main concept is you would want to create a persistent volume, and that persistent volume will request certain resources. You can have it read, write only once, or read only, and you specify how much storage you need, and then this is the persistent volume. So you'd set this one up, and then your persistent volume claim would attach to this storage. So this is an NFS example. If we wanted to, we can switch it to another different storage provider, maybe Ceph, maybe Gluster. And this is a Jupyter notebook that I'm mounting some training data in. And just one caveat about Kubernetes is currently the resource management. If you request a GPU, then your pod will utilize that GPU. You can't share a GPU with another pod. So when you do finish, then somebody else can pick up that GPU and work on it. And then, mounting volumes, you can mount your data using, persistent volumes, persistent volume claims, and that makes it very, very simple to use. And I'm going to pass it over to my teammate, Diane.
Okay, hopefully you can hear me. Can everyone hear me? Okay, great. So now we'd like to show you how we can monitor and improve an ML application using that's utilizing GPUs and the different ways you could that you can monitor your job. Excuse me, and we'll be doing this by presenting an example. And so I'm going to talk about each piece of the example first before we run it live on this other computer here. So let's see. First, I want to just talk a little bit more about why are we even using GPUs at all and why do we want to monitor them. And so has everybody here used GPUs before? Has anyone used them? Yeah, okay, so you may know some of these tools already that we're going to present. But so GPUs were initially used for the gaming industry, but the common set of instructions that are used in both gaming and neural networks makes this a really good fit. GPUs are a really good fit for neural networks as well. I used to work in the 3D graphics world for Silicon Graphics, and we did a lot of matrix math, rotating and sizing 3D objects. Now those same instructions are being used in neural networks. So this is the latest architecture from NVIDIA, the DGX2. I'm just showing it here because it's part of our demo today. The V100 is part of our demo today. We're going to use it in the cloud. And I just wanted to show just a little bit of what this looks like. A lot of times GPUs are sort of not very visible. People know how to look at what's going on in their CPU, but they don't know how to look at what's actually happening on their GPU. And you can, in the cloud, you can select maybe one V100 if that's going to solve your problem. You can select any number that you want. We ran these tests on a DGX1, which has 8 GPUs, and we also ran it on one V100. So we're also going to be presenting a model in this example that's from the new industry standard benchmark called MLPerf. It aims to represent several areas in machine learning and give people a way of comparing architectures and software stacks and see how they do. The first results have come out for this, the version 0.5 of the competition. Well, it's the official results that have been posted. We are going to be focusing on the computer vision application called Detectron, and we're going to be running that live up here. So these are the people from industry who are contributing to MLPerf, and the academics, universities who are contributing. And this is it's continuing to change as the industry changes, and so this is just the beginning. So in this benchmark, Tensorflow and PyTorch are used the most often. And Tensorflow is a Python library that is, the math is written in C++. It's for building deep neural networks, and we're going to be showing examples of this. We also are going to be showing PyTorch. Our Detectron application that we're going to run is written in PyTorch. And the input to the model that we're going to run, that we're going to train, is the COCO dataset, which in 2015, this was started by some students at Cornell and Brown, I believe, in conjunction with Microsoft. And the idea was just to have thousands of images of objects in their natural settings so that they could be detected by computer vision software. This is the output from Detectron, which is what we're going to run in a minute here. And you can see that it is able to not only identify these objects in the scene, but it labels them. There are tiny labels on all those objects. And a lot of object detection algorithms do bounding box, but this actually creates a mask, so it shows you the exact outline of the object that it's tagging. these were the initial results of the MLPerf benchmark. And NVIDIA really kind of ran away with this. They won this benchmark pretty much in every category. But so you see in the middle here, this object detection benchmark is the one we're going to run. On a DGX2, it runs in 167 minutes, and we ran it on a DGX1. It took about a little over 300 minutes to run. So these are the tools that we use. When you're monitoring one of these training runs, it's useful to see what's going on my GPUs. Are they communicating with each other? You know, what's happening here? You can run this much like the top command. You know, it's this NVIDIA SMI command. It's a system management interface command. Tells you the timestamp, the actual product name of the GPUs that you have. This bus ID uniquely identifies the GPU that you're running on. The driver version, the NVIDIA driver version. This P state is important. You can set that with the NVIDIA SMI as well. That is the power level or performance level that you're at. You want that at P0, which means that you're at the highest power use state, and you're not in power saving mode. This is the PCI link, the version you're using, and the highest version it'll accept. The temperature of the GPU, memory utilization, and so forth, the memory that you have on this machine. So the idea here is mostly people have been doing this command line view of what your GPU is doing. And what we're going to show you is a more graphical view. So when you're using Kubernetes and you bring up Prometheus and Grafana, you're going to see the same sort of statistics and the same sort of metrics, but in a graphical form. So you can see your memory high watermark much easier than just if you're just watching these numbers scroll in front of you. It's just a more user-friendly interface. So changing to another subject, another tool that you have in hand whenever you're doing your optimization is Tensorflow tracing, which allows you to see where time is being spent in your code. You just do a little bit of instrumentation here, and you're able to get a JSON file as output, which you can then display in Chrome and see where the time is being spent in your program. And if you see big gaps here, you know it's likely that you've got a bottleneck going on. So now we'll do our demo.
I got it.
Okay, so what you see here on the left is from the command line, I've just run this object detection model. I've started it up. This is the training of Detectron. And on the right, we're going to see, as it's loading in, we're going to see the GPU utilization go up. We're going to see how much memory we're using on this GPU. And all of this is, you know, you can create this yourself. It's really kind of fun to play with this Grafana interface is, you know, drag and drop, and you can create whatever sort of dashboard you want here. So here we go. It's starting to run. See the GPU utilization and the memory utilization. And in future releases, upcoming releases of Kubernetes, NVIDIA is going to be open sourcing more of these metrics. So this sort of panel is going to be the way that you're going to be, I think, you're going to be watching your GPUs in the future instead of just watching text scroll by.
And since some of the metrics are going into Prometheus, you get the alerting capability and then notifications and then different capabilities now, aside from just looking at this dashboard. You get the webhooks as well that you can push notifications to.
And so this thing runs for, like, on a DGX-1, this particular model training takes 5 hours. So you could walk away from this, walk back, you can save what's going on in the logs, but you could also just have this up on your desk and kind of see how your model's doing and make sure it's still running and using all the GPUs.
I think that's it.
So I think that's it. Does anyone have any questions?
If you have a question, please come to the microphone in the middle of the room.
Yeah, maybe I missed part of the talk, but have you guys also given some thought into configuring alerts on some of these metrics that go to Prometheus? And if you do you do it in Grafana, or do you use like a Prometheus Ansible script or that sort of thing? Or
Can you repeat the question a little louder?
have you guys thought about alerts with Prometheus for GPUs? And if you have, do you configure them in Grafana, or do you use like an Ansible script in Prometheus? Or if not, it's okay.
Yeah, I can talk on that.
I didn't understand the question.
So,
Can you repeat the question?
so I'm going to repeat your question.
Yeah, sure.
So you wanted to know how do you configure alerts in Prometheus for these metrics on a GPU,
That's right.
right? So in Prometheus, it's going to be the same process as anything you monitor. Basically, you add Alert Manager into your prompt. It's
Sure.
better if I show you the actual configuration.
Well, let me ask you this. Do you just use like a Prometheus Ansible script?
No.
Or, okay.
We just basically set up a config map, and that config map gets mounted into the Prometheus pod. And the Prometheus pod, when you mount config maps, it'll mount it as files. And you have your rules in one file, and then you have your Prometheus configurations in one file. And in the Prometheus PromQL configuration, you'd specify which alert file that it needs to read. I can give you the configuration we use for this demo.
Yeah, I'd love to see it if you have time after this.
No
Thanks.
problem.
So I have a question for the GPU metric collection. So I also cannot find another alternative solution except only are using the NVIDIA SMI. Do you guys also try to research the other tool rather than NVIDIA SMI? Because sometimes people don't trust this NVIDIA SMI metric collection.
Sometimes NVIDIA SMI.
No,
what?
our team, they don't believe they are getting 100% utilization, sometimes 100% memory. If you watch out more than last 1 year, I found that so high utilization, or is 100%. Sometimes people doubt whether this NVIDIA SMI is the right data metric collection. But I know I don't have any other choice. I'm wondering whether do you guys try to research another metric collection except for the yeah.
So this exporter actually uses NVLL, the header file.
No, but I'm trying real production more than 1 year. Sometimes this metric is weird.
Yeah.
Right?
So the library that we use uses
NVIDIA SMI.
You're talking about NVIDIA SMI?
Yeah.
Okay, is this a specific question to NVIDIA SMI?
Or any other way to, because I'm interested, how can I collect GPU metric, right?
You can use this method and just run the exporter and then export all your metrics.
No, I
that
mean,
way.
do you have any alternative idea except for NVIDIA SMI?
This is not NVIDIA SMI, by the way.
Oh,
This is using a library to connect it into the GPU and get the metrics, and then serve it as a Prometheus endpoint
Oh, right.
that gets scraped.
but
Okay,
you-
right. So we're not getting the data that we're displaying in the graph from NVIDIA SMI.
Oh,
Yeah.
Okay, that's a misunderstanding. Yeah, okay.
It is called NVIDIA NVIDIA Exporter,
It's
Node
built in.
Exporter.
If you get Kubernetes, you will get this.
no exporter is just Prometheus collector, right? I mean, how do you collect the metric?
So we run the Node Exporter.
Yeah.
It's provided by Mindprince. It's on his GitHub. He has a Node Exporter. You just run it, and you'll get all the metrics. on the node.
But you're using NVIDIA SMI to getting
No, no NVIDIA SMI. We're
no
not using.
exporter directly collect the metric from GPU?
We're using that library, the Golang library
Okay.
that connects using the NVLL header file, connects straight into the NVIDIA GPU and shows the metrics.
Oh, okay.
So NVIDIA is exporting it for Prometheus, not for the command line.
Okay, got it.
Okay?
Yeah. Yep.
Sure.
So in the graph, like you were kind of. So in the graph, you were kind of seeing around 60%, 70% usage of the GPU. How do you debug where the bottleneck is? How do you make it go 100%?
How do you figure out how do you get it to go up? Okay, so one thing you can do in this particular benchmark that I've done is change the batch size of the number of images that you're sending it. So that's one thing. Also, I'm trying to think. So that actually worked for me. I just changed the batch size and was able to get it to. And also, in this example, it's only using about half the memory on that GPU. So when I increased the batch size, then it also was using more of the memory.
Thank you.
Yeah. Another way, actually, there was another way. This particular benchmark uses ResNet 50, and I used a different version of weights for ResNet and got better utilization with that as well.
So for the utilization, can you get down to more detail, trying to show whether it's single precision or double precision?
Sorry, can you repeat that?
Oh, you want to see what precision floating point
Yeah.
you're using on the GPU
Yeah.
graphically? I think that would be in an upcoming release. It doesn't tell you that now.
Okay.
Yeah.
Are there any?
It'd be good to know, though. I understand. Yeah, I understand what you're saying.
Okay.
Yeah.
All right, everyone, let's give him a big hand.
Thank you.